A major appeal of the LHC, which has brought it recognition far beyond the particle physics community, is the sheer bigness of both the experiments and the questions they're designed to answer. This is certainly true of the ALICE detector, which is designed to recreate the moments just picoseconds after the Big Bang. I'm here inside the CERN Exhibition Centre with David Evans, head of the UK ALICE team, to find out more. Nice to meet you, David.
Nice to meet you, James.
So, what is the ALICE detector and what's it designed to do?
Okay, so the ALICE detector, this is a picture of the ALICE detector during the construction stage. So it's a 10,000 ton detector, 16 meters wide, 26 meters long, so it's a massive detector.
Huge project.
With a giant magnet around the outside, and then the inside has this onion structure of different types of detectors that measure the properties of particles.
So this is the magnet.
This is this giant, yes, there's more iron in this magnet than the Eiffel Tower. It really is a ginormous experiment.
So what is ALICE designed to look for?
Well, ALICE, as well as colliding protons throughout the year, at the end of the year we collide lead nuclei. So we take all 82 electrons off lead atoms, accelerate them in the LHC to the maximum energy, and we collide them together inside of ALICE. When you have these collisions, they're incredibly violent, and thousands of particles and antiparticles are produced. So ALICE had to be designed to really cope with those kind of extreme conditions.
So what do you actually, within the detectors, what are you looking for? How is it designed to try and capture these collisions? What aspects does it have that are different from other detectors?
Well, what happens is when we collide these lead nuclei, we create a tiny subatomic fireball which really recreates a little bit of the first instance of the universe. And that only lasts for a fraction, a moment, before it turns into lots of particles and antiparticles. So we don't measure the fireball itself, we measure what comes out and extrapolate back. So really, this has to cope with those thousands of particles. So in the center of the detector, this is not here at the moment, this is a picture in construction, we have what's called an inner tracker, which is made of silicon pixel detectors and strip detectors, and that can cope with the very high density of particles. As we go further out, we have our main tracker, which has a rather exotic name called a time projection chamber. But it's not actually a time machine, unfortunately, but it does then, it's a detector that's designed to cope with a very, very large number of particles.
You said that you ran it at the end of last year with lead collisions. Have you discovered anything new since then?
Yeah, already. I mean, the fact that we only ran this in November and December, already the first results have come out, and they've been quite surprising. This fireball that we create, I mean, it's about 10 trillion degrees and almost as dense as a neutron star. So it's a little bit like the early universe was, just before protons and neutrons were formed. And we believed that the early universe would behave a bit like a gas, with these quarks and elementary particles moving around like a gas. Our results show that it behaves more like a super hot, dense liquid. I mean, this is no liquid that most people are familiar with. You're talking of a 10 trillion degree super dense liquid. But we've already discovered that coming out of that, and a few more surprises where our model that suggested what's going on, our results are different to the model.
So that's something that wasn't predicted by the theorists then, this ultra-dense liquid?
No, I mean, it was a surprise from a previous experiment that was running at much lower energies, but we still believe that these high energies, at factor of 10 energies, it would start to behave like a gas, and it still seems to be behaving like a sort of ideal liquid, so that was a big surprise.
So is that kind of the main idea, the main science behind it, is to recreate the moments after the Big Bang?
So, yes, because actually by creating this exotic state of matter, which is called a quark-gluon plasma, we learn a lot more about how the strong force works. So that's really, so a byproduct is we learn how the universe evolved at that very first stage before particles that we know about, protons and neutrons, existed. But what we really learn is how this strong force behaves. Really with the strong force, I guess we're at the state now where perhaps people like Faraday, etc., were in the 1800s when they were studying the electricity of magnetism. We now understand that force very well. Now we need to understand the strong force.
You're saying it's the strongest of all the forces. I mean, can you give some kind of everyday comparison just to illustrate how strong
Yes,
it is?
I mean, on the atomic scale, if you think of the force between the electrons and the protons, the electromagnetic force, the strong force is about 1,000 times stronger than that. So, if you think of a nucleus with all those positively charged protons crammed together, surely the electromagnetic repulsion should push it apart. But the strong force is so much stronger, it holds nuclei together. Without that, we would all just explode.
Quite important then. So what next then? I mean, do you plan to run again and at higher energies this time?
Yeah, so we've only just started. We did a lot more statistics, and we also need to collide proton physics because the design of the detector makes it rather ideal for studying certain aspects of proton collisions as well. So we have that. We have a program that will last at least 10, 15 years. So next year we want to increase statistics by a big factor with not just proton but lead collisions. After that, we might do something a bit more exotic, like proton-lead collisions, to actually study some nuclear effects. And then there will be a CERN shutdown where we'll double the energy, and then we'll actually look at even higher energies and see what's going on.
And finally, I mean, as a physicist, so you're the head of the UK team. I mean, for you, what's the best aspect of working at a place like CERN, a big international centre?
I think it's a really exciting place to work. I mean, you spent the day at CERN, you can see the sort of energy there is at CERN and the excitement. So it's great to work with an international community of very bright people. But the other thing is working on an experiment where we know we're going to find new physics, but we don't know exactly what that new physics will be. And it really could take our understanding of physics down a different path. Well, that's really exciting for me.
Exciting times. Okay, well, it was nice to meet you.
And you, James.